I love diffusion models, but they are quite annoying because they take up so much time to generate an image. But distilling diffusion models is kind of becoming like a research area where you kind of want to distill like diffusion models into a few steps as opposed to 1,000 steps. So normally with a diffusion model, so I'll just go through basic idea like usual. You will have, say, your image here, and yeah, this will be your image x0, and this will be at time 0. And you usually have a bunch of steps to do this. So yeah, just do it in black. You would then take a step, x1, and then that would add a little bit of noise to the image. So it just adds a little bit of noise, like so. And then you do this again, and this would be time 1. This would be time 2. So you do this again, and it adds even more noise. So it adds more noise on top of x1. So that would look maybe like this, x2. And then you do this over and over again until you get an image that is pure noise. So this is just pure noise, like that. And this is x sub big T. And this would be T is equal to big T. So usually, so it depends on how you train this, but if you're doing a discrete way, then let's say this is T is equal to 1,000. So if you discretize this, then T is equal to 1,000. And that means that it takes 1,000 steps to sample this. Now, you train a model that basically reverses this process. So it looks like this, like so. Yeah, and this model, we'll call it, maybe we'll just call it M for diffusion model, M theta. So M theta basically reverses this process, like that. And basically all you're doing is you're saying, I have this model here, and this model at any time step, so M theta, M theta of some time step, so of some image at some time step, and the time step, so you inform it of the time step, is going to be equal to the previous time step. So basically you just train it to denoise the image one step at a time. Now in reality, you actually do it the other way. You basically tell it to predict the noise. So this will be epsilon at time t. So epsilon is just the noise you have at any time step. Now, at any time step, you basically have x sub t is an interpolation. So x sub t is equal to, I'm not going to worry about the normalization and stuff, but it's basically like 1 minus alpha t times x0 plus alpha t epsilon. And epsilon is just sampled from a Gaussian. Now, in this way, if you have, say, alpha t is equal to 0, or alpha 0 is equal to 0, then you have full signal from your original image, and you have no signal from your noise. And then if you have alpha is equal to, say, big T, which is equal to 1, then you have 0% of your original image and 100% of the noise signal. So yeah, your model basically just learns to remove the image part of the image and give you the noise at any time step. Now, like I said, this is annoying because you have, say, 1,000 time steps if you discretize this process. In reality, you don't actually discretize it. You have a SDE, but it still takes a lot of steps. Or you have an SDE to go forward in time to basically add the noise, and you have an ODE that basically reverses this to remove the noise, because once you've added the noise, it's deterministic to remove the noise. I'm not going to get into the math about SDEs and ODEs and how this kind of works with diffusion models, because this paper is not on that. But yeah, just think about it like you have a lot of steps and you want to distill it. So they basically want to distill it, so there's only 4 steps. So that's pretty good because current samplers, like you can reduce 1,000 steps down to say like 50 with DDIM if it's discretized. And if it's not discretized, you can get it down to like 20 steps. But 4 steps is even better, especially if the quality is better at 4 steps once you distill it. So that's the method. Basically, that's the idea. They want to take this 1,000-step process and distill it into a 4-step process. So yeah, quite a distillation procedure, but it's actually quite easy. And this image is actually a really good image. So if we look here, let's see. So basically, you have a student model and a teacher model. Whenever you're doing distillation, you usually have a student-teacher model. So your teacher model, they use Stable Diffusion XL and Stable Diffusion 2. I think they're mainly trying to get Stable Diffusion XL compressed. So this is Stable Diffusion XL. This is trained. And your student is also a trained Stable Diffusion model. Basically, you initialize both of these, both of your teacher and your student model to Stable Diffusion XL. You initialize them to the base model. Now, to train this thing, basically what you're trying to do is somehow, so the idea isn't to make the student model small. The idea is to keep the student model the exact same size and just reduce the number of time steps that it needs to sample. So the idea is to kind of, if I go back to this chain over here, it's kind of like if I have these first, I guess if I had this chain here and maybe this part represented the first 25%. So instead of this being 3 images, maybe you can think of this as say 250 images instead. So 250 images to sample this, 250 steps. So instead, you just want to make that 1 step. That's what you're trying to learn. You're just trying to distill a lot of steps into 1 step. It's not reducing the size. So basically, what you do, remove this, is here 1,000 steps, 1 step. So your teacher trajectory is going to be 1,000 steps long, while your student trajectory is just going to be 1, 2, 3, 4. That's all it's going to be. Now, to train this, you basically take an image from a data set. So whatever data set maybe Stable Diffusion XL was trained on, and you noise it. So this is your normal procedure. You add some noise, like usual. So you just add a little bit of noise to X0. You get a noisy image. And with normal diffusion training, you basically, at a random, you go to a random part of the chain. So maybe I go here, and then I ask it to denoise that. Ask it to give me the noise in that part of the image. So you basically just noise the image, and then you send it through the student model. The student model then produces the output image. This is implicitly defined by the noise, because if I subtract the noise from this image, then I get this image here. So basically, your student model is still predicting the noise at time step t. It's predicting the noise, but it's implicitly predicting the actual image. So you can get this reconstruction pretty easily by manipulating the formula here. So your student model then basically makes a prediction for what the reconstructed version of this is. Now, it's obviously not going to be perfect, and whenever it starts, it's going to be pretty good, because whenever it starts, it's initialized to Stable Diffusion XL. So it's not just going to produce garbage output. It's going to produce some good-looking output. And you do this since you do this for like 1 step, so you're only having this predict this in 1 step, or 2 steps, or 3 steps, or 4 steps, this prediction is going to be pretty good, but it's not going to look that good. You then noise this image, and then the teacher model then basically fixes the image. So the teacher model has access to all its time steps. So it produces a really good image because Stable Diffusion XL does that. While the student model is going to initially produce a really, like, it's going to produce an image that may look like this, but it's not going to produce an image that looks good. It's going to be probably very flat, very plain. There's not going to be a lot of detail to it, but it's probably going to have the base there. So yeah, that's the process. And then you have two losses. So I think the reason why they take the output of the student and they put it through the teacher as opposed to taking this and putting it through the teacher is because you kind of want the teacher to tell it how to correct itself. So if you think about image to image, if you add a little bit of noise to this, which is what image to image does, you can kind of like correct the image. So it still has the same base. And this would be kind of the correction for this image here. Now, the losses are pretty simple. I'll scroll down here for the losses. Here's the first loss. So this loss is basically just the reconstruction between the teacher and student. So this is our student. The student predicts an image the student makes a prediction for the image, and then this is the teacher model, and the teacher also makes a prediction for the image based off what the student predicted. So it's just, and you just do L2 norm between that, or not L2 norm, mean squared error between that. So your distance function, they just use MSE. You then have a weighing function here. So if we go up here, they say, yeah, we just use MSE. What else? What did you expect? Do you expect them to come up with a different distance function? No, not happening. They also say that they pick CT is equal to alpha T, where higher noise levels contribute less, and score distillation sampling was another method that they had, but they use this. They use CT is equal to alpha T, where higher noise levels basically contribute less. And I think this is what they used in the original DDPM paper, where you had this coefficient out in front of the loss. They didn't end up using it, but they had a coefficient out in front of the loss where the higher the noise level, the less that contributed to the loss. So this wouldn't contribute to the loss as much as this when your model is making predictions. So yeah, they just use some weighting function. Yeah. So that is the reconstruction loss, basically just saying the student and teacher prediction should be the same. And this makes sense because this model here is going to make a prediction, a prediction with a random time step, so 1, 2, 3, or 4, and you just want it to reconstruct that. Yeah, pretty basic idea. Always have a reconstruction loss. One thing to note is that the noise here and the noise here are different, and obviously the time steps are going to be different. This time step is in between 1 to 1,000, so the noise here, it goes into a random part of the chain, and that part of the chain can be 1 to 1,000, and then this part here can be 1 to 4. So the noise here is or the discretion for the noise here is much greater because you only want it to produce something in 4 steps, or 1 step, that is. So one other thing to note is that this is able to be done. You can differentiate 4 steps. 4 recursive steps in a model, that is okay. You can differentiate that. You cannot differentiate this model here because let's say it takes 1,000 steps to make a prediction in the image. That would be you would run into the RNN problem where you have vanishing and exploding gradients. So you basically just have a stop grad here, and it doesn't get signal from the teacher itself. It kind of indirectly does with the loss, but that's fine. That works well. And that's one important thing I thought I should note. Now, there's also this adversarial loss here, and this is actually really important. The adversarial loss, they'll show later. It's very important, but yeah, you just send this through a discriminator, and this would be your real image, and this would be your fake image, and then it tells you if it's real or fake or not. Normal GANs, so this is basically like GAN loss. You have your real image here. So you have a real image, and then you have some noise. You feed the noise through a generator, and this produces a fake image. Then you throw both of these through a discriminator, and the goal is for the discriminator to say, well, this is real, this is a 1, this is fake, this is a 0, and the generator basically wants to fool the discriminator, so it wants this to be as real as possible, trying to make the discriminator pick a 1. In this case, our generator is our diffusion model, what is it, theta, and our discriminator is just phi, so we'll get into what the discriminator looks like in a sec, but yeah, it's just normal adversarial loss using a discriminator. Now, the adversarial loss is, yeah, it's just normal adversarial loss. They use this loss here, I think. Yeah, they use this loss. So if we go through it, basically this is your generator's loss. Your generator is trying to maximize the expected value over, we'll get into what the heads are in a sec, but basically over the discriminator's output on the fake images, or the discriminator's output on the fake images. So the model produces a fake image, and the discriminator gives a score, and you want to maximize the expected value of that score. Now, the discriminator is the opposite. So if we look at this first term here, it's the expected value over the discriminator on real images. So it wants to maximize that. This term over here is basically the opposite of the generator. It wants to minimize the score on the generator. That's all. So this is like nothing too special. It's just a GAN. So they also mentioned that they need an R1 grad penalty. They find that the R1 penalty is particularly beneficial when training at output resolutions larger than 128 pixels. So just some normalization to make it look good. You needed this in WGAN. You usually need this to make GANs work well. It's not a GAN, but it uses a discriminator, and that probably just makes the loss landscape look better. So that the model actually learns. So that is the adversarial loss. It's pretty normal. They have this part here though, which is k-heads. So this is different from usual. Usually you just throw it through a discriminator. Sorry. Usually you throw it through a discriminator and it outputs a value. So that would be 0 or 1. Where's the picture? Yeah, so it outputs a value that would be 0 or 1, and you just differentiate that to update your model here based off the signal coming from the discriminator. Now, they use something slightly different. So the way they create the discriminator is different from usual. You don't just throw like a convolutional neural network at it. So the procedure, they actually throw a VIT at it. I think it was Dino V2. So the procedure looks like this. So I have a real image here. So this is the real image. This will be the predicted real image by the model. So this would be predicted by theta. So theta would give us this. I guess that would be theta of xt is equal to that. Now this is, oh no, this is a fake image, sorry. This is the real image, so this is just real image x0. Now the fake image would be given by theta. So a fake image maybe it looks a bit weird. There we go. Weird looking cat. This would be our fake image, and this is theta of xt is equal to x0, x0 hat. So the prediction, and you now have this VIT. So a VIT just has a bunch of blocks in it, and these blocks will be frozen. So this will be like B1, B2, and so on. I'll put B3 as well. B3, and you just keep going. So it's just a transformer, a stack of blocks. Maybe this will be B end. I don't know. You just have a bunch of blocks. Normal transformer VIT. Now uh, you also have other conditioning. So you do send these both through the model, and I'll get into conditioning in a sec. But you do send these both through the model, and you get an output from the model out here. But that's not super useful. Instead, what they do is they take the intermediate outputs, the latents, or rather the hidden states, and they put a head at each of these. Well, I don't know which spots they put them at. They say they put them at spots. They don't say which ones, but you take the intermediate outputs and you put a head at each one, so or a head at various ones, not at each one, H3, and so on. Now, each of these heads basically is trainable. So this is your base VIT. This is a really good feature extractor. It already has a ton of knowledge of what images look like, and each of these intermediate states has some intermediate feature extraction from those images. And you're basically you're probing those intermediate hidden states and getting information from there. This has kind of been done before, where you kind of just probe a discriminator network, and then each of these basically gives you a loss. This would be L, 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 2, 3, or rather, it gives you like a discriminator value at each of these hidden states. So 1, 2, 3, and each of these is part of your loss. So you would have K of these, and that's what so you basically just average over all this. And yeah, you basically want these intermediate states, which have a very good feature representation, to be equivalent. Now, they also mention that they don't just do this, they actually condition the model so that it has more information. This would be Dino. So they use a Dino model to condition the model. You can throw x0 through here. So no matter what, they condition on x0. And this gives you C image. So it's conditioning on the original image. And you can condition the blocks on there, or yeah, the transformer blocks on there. And you can do that by just adding cross attention, and maybe you make that learnable. They also do this with text. So you have C text, and this is done with clip. So you have this frozen clip model, you have a frozen Dino model, and this gives you the discriminator more information to work with. Picture of a cat. And yeah, you just condition the blocks on there. And this way the model knows exactly what the original image and what the text was making. Hopefully a stronger signal. And yeah, that's their discriminator. So the discriminator isn't actually like this trainable big model like they show here. It's actually a pre-trained VIT with probes. We can go down here. Yeah, so the trainable discriminator heads are applied at features at different layers of the feature network, which is Dino. And then they say commonly a text embedding is used, but in contrast to standard GAN training, So in GAN training, you may condition on CText. The conditioning configuration also allows to condition on an image. So don't worry about that. Therefore, for a given generated sample, we can condition the discriminator on information from X0. So you just condition it on X0, knowing what the actual original image was when it was given the fake image. And this encourages the student to utilize the input effectively. It just has a better signal from the discriminator, probably. In practice, we use an additional feature network to extract an image embedding. Yeah, so that is the model, basically. It's pretty standard model. Just the distillation loss, and then the discriminator adversarial loss. Now they have some interesting parts, ablations here. So what is the objective? So what is the backbone for the discriminator? They find that Dyno v2 works best, as shown here. Then what do you want to condition on for the discriminator? They find that if you condition on both text and image, it does pretty well. If you don't condition on either, it also does pretty well, but it does a lot better if you have both the text and image. So initialization, what do you initialize the student model to? Random is garbage. It's not good at all. Pre-trained is good. And this makes sense because the output of the student model is going into the teacher model. And if this was just pure garbage, then this output here is probably going to be garbage. It's probably not going to be that good. And you don't get much training signal for how to improve your image. And also, you're starting from nothing, so it's quite difficult to train. You're basically training this from scratch if you start from nothing. But if you start from Stable Diffusion XL, it already knows kind of how to generate an image in 1 to 4 steps, but not too well. You're just kind of improving upon that. And then this part here, which is just, if you just use adversarial, it doesn't do that bad. If you just use distillation, though, it does really bad. And then they just use the exponential part for the distillation loss, the weighing term. Other than that, I don't think there's not much more here. So basically, you're just making this, you're just distilling this into 4 steps, and it's really fast at generating. Go ahead and check this model out. They have it open sourced because it's by Stability.ai, so they're going to open source it. Yeah, they have the weights, obviously, and the code, which is very nice. So yeah, that's the model. Pretty cool that you can now generate things in 4 steps, and the quality doesn't really suffer very much. And yeah, I don't think they really even trained this for that long. So cool approach for doing this. Yeah, but that is the paper.